copy this. How's it going? Are we live? Hey, we're live. How you doing? So we've gotten through all of the main rules for testing series for convergence. We know the integral test, we know comparison tests, we know the divergence test, we know the alternating series test, the ratio test, the root test, and we know these three specific examples: the geometric series, the p-series, the harmonic series. I'm copying this down because this is the idea that we want to do a bunch of examples with today. So let's do that. Here is an example. Consider the sum. Oh, let me show off before I get too deep into this. Do I have this still posted? I don't. Hey, there's the homework assignment. Let me show you what the instructions are the main thing for this test are. The main instructions are: determine if the series converges or diverges. If it's also an alternating series means it has a -1 to the n on it. You need to, just converges is not enough. You need to say if it converges absolutely or conditionally. If you use a convergence test, say what test you're using, show that the necessary conditions are satisfied. That means you need to know what the conditions are. If the series happens to be geometric, also evaluate it. Let's talk about, let's just do this example. Let's do the sum of 1 over n log n log n squared. Where should this thing start? The function log n is undefined. Log n is undefined at 0, which means log n is undefined at 1, so I need to start this series at 2 at least. Because I can't take log 1. Because log 1 is log 0 is undefined. Cool. Let's talk about this series. How do I do this series? What would I try? I got all these tests. The comparison tests are usually the biggest ones. I want to try and understand about how big is this thing on the denominator. If I have like n plus things that are smaller than n, I say n is bigger. N goes to infinity pretty slowly. Log n goes to infinity even slower. And log n goes to infinity so slow. If you take log of a million, you're taking log of 6, you're getting like 2. If you take log of a million, you're getting 9. Take log of that, you're getting like 2.5. These numbers, the function log n, technically goes to infinity because you're taking log of infinity. But the idea is that log goes to infinity very, very slowly, which means log n goes there even slower than that. And it's like these things compound on each other. You want to say exponentially, but it's like the opposite of exponentially, or maybe, I don't know if that's the right thing, but the more logs you stack on, these things go to infinity so slow. So it's really normal to look at this and say n times log n. You've made n bigger, because log n does go to infinity, so this thing is technically bigger than n, but just barely bigger than n. You throw in a log n, now it goes to infinity, again, even bigger than that, but so much, the amount much bigger is so small, you sort of expect that this thing should be about the same size as n, right? It's technically a little bit bigger than n, but not much. So 1 over it should be about as big as 1 over n. And what does the sum of 1 over n do? The sum of 1 over n diverges. That's the harmonic series. So it's pretty reasonable for our first guess to be that this thing probably diverges. And it might be reasonable to try and do some kind of comparison test with 1 over n. I want to think about, can I do the easy comparison tests? The easier one is direct comparison. To do direct comparison, and end up showing that this thing diverges. I'm right now operating under the assumption that it's going to turn out to diverge, because I'm thinking it's about as big as 1 over n. If this thing diverges, then to use direct comparison to show it diverges, I would need to show that 1 over n log log n would have to be bigger than 1 over n. Is it bigger than 1 over n? Its denominator, log n, is big. Log n is big. This denominator is bigger. That means the fraction is smaller. Crud. Being smaller than infinity isn't helpful at all. So that's not going to work. I can't use direct comparison with 1 over n. Often when direct comparison doesn't work, we try limit comparison. Let's try the limit of 1 over n log log n over 1 over n. This is the limit, as n goes to infinity, of n over n log n. Oh, I missed the squared on these. Log n squared. The n's cancel. We get the limit of 1 over log n log n squared. And that limit is 0, which is not helpful. That says that the top of this fraction is materially smaller than the bottom. It's smaller in a significant way. It's like a 1/0 of the size of the bottom, which means that I know that this is smaller than this, which is the thing I already knew. It didn't work. I need to know that you're bigger than infinity to show that you're infinite. So direct comparison doesn't work either. What else could we try? I could try, I guess in theory I can use the root test, but thinking about the nth root of 1 over n log n, I don't think that's going to simplify. And even if it did simplify, the root test is something that works when the thing is basically geometrical, and this thing does not seem geometrical. 1 over n goes to infinity much slower than something that goes to infinity exponentially. And this thing is only going to infinity a tiny bit faster than that, or is going to 0 a tiny bit faster than that. The terms are going to 0 a tiny bit faster than that. So probably if the root test and the ratio test don't work on 1 over n, and they don't, then they're probably not going to work on this thing either. So that's not looking good. What else can we do? If I go back to my list of tests, what haven't we tried? Ratio test, root test don't look like they work. Alternating series test, this thing's not alternating. Log n is eventually positive, so is log n, so that's not going to do anything for me. The only thing we haven't tried is the integral test. The divergence test doesn't work, because the terms do actually go to 0. I guess we can still try limit and direct comparison with other series that we understand. But I don't have any really good potentials, so we're going to try the integral test. Consider the integral from, what would it be, 3 to infinity? I want the base to be after the thing is positive. When does log... Oh, I guess that thing's always positive because it's squared. Let's push it out a little further. I don't want to deal with the thing being undefined at any points. When does log x equal 0? When log of x equals 1, that's when x equals e. So as long as we start after e, the denominator will never equal 0. Okay, so 3 is fine. The integral from 3 to infinity of 1 over x log x squared. Do I have any chance at integrating this thing? Oh, you do the substitution u equals log x. That does something, because du is 1 over x dx is out there. This integral turns into the integral. I got to change the bounds of integration. That was x equals 3, so that's u equals natural log 3. That's x equals infinity. Log of infinity I'll read as infinity. Technically I should be writing these things as limits, but we're not in exam 1 anymore, so it's okay to say that the integral from here to infinity does equal the integral from there to the infinity. So this turns into, this stuff all becomes du. I want to, in case this is going to turn out to be part of my paragraph, I want to try and write this pretty cleanly. I get 1 over u log u squared du. Again, I like the substitution v equals log x. dv will be 1 over, v is log u. So dv is 1 over u du. Again, I have the 1 over u du. Now I get the integral from log 3 to infinity of 1 over v squared dv. And now I can actually do the integral. Go away. That's the integral of v to the negative 2. Actually, I'm going to go ahead and just stick that in here. The integral of v to the negative 2 is negative v to the negative 1. I need to evaluate that from log 3 to infinity. This is, I'm going to write this in a thought bubble because it doesn't actually make sense to say that's negative 1 over infinity minus negative 1 over ln 3. Saying that this thing equals negative 1 over infinity is not the correct way to do it. It's a limit at infinity. I guess I'll go ahead and write the correct way out, since that's what I'm supposed to be doing with these examples. This is a limit as a beta or a capital B goes to infinity of negative 1 over b minus negative 1 over ln 3 equals 1 over ln 3, which in particular is not infinite. Cool. The integral test worked. We were able to do the integral, which gives us an answer either way. If the integral was infinite, we'd be done. If the integral was finite, we'd be done. We do need to know that the hypotheses of the integral test work. Maybe that's something we should have checked out beforehand. What do I need to know for the integral test? Check and see if you know the answer to that question. You want to know the answer to that question before exam day. The thing we need to know for the integral test is that the function is positive and decreasing. This thing is eventually positive. We've jumped. Going past 3 means we're past the places where these things are negative. They don't equal 0 anymore. They're going to stay positive forever. How would I best show that the thing is decreasing? I could take its derivative, but that doesn't look fun at all and looks way too gross to be a good explanation. I'm allowed to get away with something else, since the functions x, log x, and log x squared are all eventually positive and increasing. We have their product, x log x squared, is increasing and positive. And so f of x is 1 over that. Is decreasing. This function is built out of functions I understand, so I understand some things about it for free. Cool. It's decreasing and positive. Since the integral from 3 to infinity of that function... Oh, I should say, the reason I care that it's decreasing and positive, like I shouldn't just let that sentence float out there like automatically everybody understands why I care. The reason I care that it's decreasing and positive is that's what lets me use the integral test. So the integral test works, or the integral test applies. Or so we may use the integral test. You got ways of phrasing this. There's still... I'm putting so much effort into nitpicking these word choices, but you're still allowed to have some personal style in here. You can phrase these things the way you want to. So we are allowed to use this test. So I guess saying allowed to feels a little bit juvenile, but it's okay to talk a little juvenile sometimes. The integral test applies is a super fancy way of saying it. It makes me feel like a grown up. I like doing that one. Saying that it works feels, I don't know. You know what the word works means. The integral test applies. Since the integral from 3 to infinity of f of x, I don't want to write out the gross function, I just gave it a name, so I can use that, is finite by above. It follows that the given series converges. Cool. Here's a place where our intuition was wrong. N log n squared is only a tiny bit bigger than n, but it's bigger enough to make the difference. 1 over n, the sum of 1 over n diverges, but it sort of... It makes sense to think of this as sort of being on the borderline. If I think about 1 over n is bigger than 1 over n to the p with p bigger than 1, which all converge. Those are convergent p series. And it's smaller than 1 over n to the p where p is less than 1. And these things all diverge. So 1 over n is sort of right on the borderline. This thing diverges, but just barely. And it is a fact that if you have a sequence that goes to infinity, no matter how slowly, no matter how insignificant this thing that goes to infinity is in your head, it is possible for that series, for that sequence, to make the difference, if you multiply it on, between convergence and divergence. And that's sort of what we just saw here. We only did the integral one way, but if we had the integral of 1 over x log x not squared, that'll turn into the integral of 1 over v from somewhere to infinity, which will be natural log of infinity, which diverges. So the fact that that squared there was the thing that made the difference between converging and diverging for this problem. This log x, if only one of those log x's was there, this thing would diverge. The log x, even though it goes to infinity very, very slowly, is still big enough to make the difference and push you over the brink to converge instead of diverge. By and large, these things that are down here in the right at the borderline, the integral test is the most powerful thing you have for these functions at the borderline. There are a lot of versions of problems where you have a 1 over n with a bunch of logs and a bunch of whatevers, where the integral test is basically what you need to do to figure out whether it diverges or converges. Compare that with the sum from n equals, I'll figure out what the base is in a second. Let's try 1 over n squared log n to the 5th log n. Our intuition last time turned out to be wrong, but that doesn't mean we shouldn't try to use our intuition. I still want to try to understand how big this function is at its basic. I think if I start at 3 again, this is okay. About how big is n squared log n to the 5th log n? It's probably about as big as n squared. Those logs are significantly smaller than an n squared, so they're probably not contributing that much. So 1 over this should be about as small as 1 over this. And what does the sum of 1 over n squared do? That's finite. It's a p-series. Or it converges. meaning that the number it converges to is finite. So this one, my intuition should be that you are finite. And this time, because the denominator got bigger, the fraction got smaller. Oh hey, we're in the good situation, where the thing automatically converges because it's less than that. Is that right? Yeah, since log n and log n are eventually large, we have that 1 over n squared log n to the 5th log n is eventually less than one over n squared. Cool. So the sum of 1 over n squared log n to the 5th log n converges by direct comparison with the convergent p-series sum 1 over n squared. There's a couple things that didn't get said that maybe this paragraph would be better if they did. To use direct comparison, I need to say those things are positive. How come I didn't say that the things are positive? Well, mostly if things are positive, it's obvious that they're positive. I did already point out that these things are eventually large, and part of being large is being positive. So that sort of got mentioned in there. Although maybe I could have found a way to squeeze that in and had a stronger paragraph because of that. What else didn't I say? One thing that I want to be clear on is that when I'm doing the comparison, like the thing I'm stating, I used a sentence because the math was already pretty gross. 1 over n squared log n to the 5th log n is less than 1 over n squared. This is the thing that I wrote out using words instead of an inequality display. I want to make sure I'm talking about the terms of the series, not the sum. It's true for the sum, but the condition of the reason I'm allowed to use the direct comparison test is because the term is less than the term. The term less than the term is the hypothesis that I want to show. The sum less than the sum is like one of the conclusions you get from that. I want to make sure I'm being clear that I'm talking about the terms, not the series. Talking only about the series means jumping to the finale, where you're using the direct comparison test before you verify that you can use the direct comparison test. The reason I'm writing it out because I'm trying to verify that I can use the direct comparison test and not immediately saying the conclusion. I said the words direct comparison. I didn't mention that 2 is bigger than 1 is the reason that I'm allowed to do that, but that's the kind of thing that you don't really need to say. If you know the word p-series, then you know it converges when p is bigger than 2. Maybe, but the paragraph would be better if I mentioned that. I'm looking for excuses to prove that I know what I know, and squeezing those in. Yeah, let's throw that in. P equals 2 is greater than 1. Is enough of a little mention there. This is kind of sloppy. Maybe it's better to make that a full sentence of explaining why I'm talking about what does p equals 2 greater than 1 mean. I'm not being very clear there. But this is the kind of baby little step that I feel like I maybe don't need to include at all, and it's okay to just sort of give someone a little reminder of why you're allowed to do something. Okay. I want to try something very close on the other side this time. Consider. How about the sum from n equals... I'll figure out what the base needs to be in a second. Let's try 1 over N to the 3/4 log n to the 6. I got tired of writing all those log n's. I'm going to make this one a little simpler. How big am I allowed to plug in? I can't plug in 1 because then I'm dividing by 0. This series is allowed to start at 2. Let's start it at 2. Again, I'm thinking about how big is that? N to the 4th, n to the 3/4, log n to the 6. That's a bunch of log n's, but log n is so small that really this should be about as big as n to the 3/4. It's not the exact same size. The ratio doesn't go to 1. This log n does go to infinity, so the left-hand side is materially bigger than the right-hand side, but materially bigger by such a small amount that I don't expect that small amount to make much difference. That means 1 over this and 1 over this should be about the same size. You have a bigger denominator, so you're a smaller fraction. What do I know about 1 over n to the 4th? I know the sum of 1 over n to the 4th, n to the 3/4, diverges. So I'd like to show that that thing converges. Wait, so I expect this thing to diverge also. To show something diverges, I have to show that it's bigger than something that's infinite. I have that it's less than something that's infinite. So direct comparison won't work. I was hoping, if I'm hoping to show that this thing is infinite, then I'm hoping to show it's bigger than something that's infinite. And I don't have that. I am smaller than something that's infinite. Can I try limit comparison instead? Well, I just said that this thing goes to infinity, so the left-hand side is still materially smaller than the right-hand side, so limit comparison won't work with 1 over n to the 3/4. So here's a place where it feels like I'm kind of stuck. I want to take a break for a second and think about, in a little more detail, some of this how big and how small stuff. I want to talk about things that go to infinity. Or sequences that go to infinity. We sort of have n here in the middle. The reason I want n to be in the middle is because the sum of 1 over n is sort of like the borderline between things that converge and things that diverge. N is an example of polynomial time. N is smaller than n squared and n cubed and n to the 4th and so on. These would all be called polynomial time. By the word time, maybe a better word is speed. They go to infinity as fast as a polynomial. This includes things that aren't polynomials. If I think about n squared log n, that fits in between n squared and n cubed. It's not a polynomial at all. If I tried to write f of x as x squared log x, that does not count as a polynomial. But in a certain category of, like, if I'm thinking about the speeds at which things can go to infinity, if this goes to infinity a little bit faster than n squared and a little bit slower than n cubed, he's between two polynomials, so he fits into the family of polynomials. What goes to infinity faster than polynomials? You can talk about exponentials. So that would be like 1.01 to the n is a very slow exponential that goes to infinity. And 100 to the n is a very fast exponential that goes to infinity. But they are all exponential. And the meaning of this chart is anything exponential is faster than anything polynomial. You have a very big polynomial that goes to infinity and a very small exponential that goes to infinity. The exponential is bigger. This is part of what people mean when they say exponential to indicate, oh, that's so big. It's bigger than a polynomial. It's not the biggest there is. Bigger than any exponential is n factorial. N factorial, like 5 factorial, is 1 times 2 times 3 times 4 times 5, is eventually going to be bigger than 100 to the n. We'll do an example comparing 100 to the n and a factorial. But the n factorial on bottom will eventually be 1 times 2 times 3 times 4 times ... times a million. Once we get to 100,000 factorial, this will be a bunch of numbers from 1 to 100,000 multiplied together. The thing on top is a bunch of copies of 100 multiplied together. So I'm thinking about the 100,000th term of each of these series. I was going to make it the millionth, but I didn't write enough zeros. 100 to the 100,000 versus 100,000 factorial. They both consist of 100,000 things multiplied together. And the key thing here is most of these numbers are bigger than 100. None of these numbers are bigger than 100. At the start of the sequence, the 100 is bigger, right? The fact that the 100s are all bigger means 100 to the n looks like it's going to end up being much bigger. But once you get past 100, this guy's getting factors that are bigger than 100. And eventually they're getting much, much bigger than 100. And they will eventually get enough bigger than 100 that the n factorial is going to win over the 100 to the n in the long run. When I talk about a sequence being bigger in this chart, I'm talking about in the long run, which one is going to be bigger. And n factorial is bigger than any exponential. Is n factorial the biggest it gets? No, you can talk about n to the n. Again, there's n things multiplied together, but now they're all the biggest number and not just working their way up to the biggest. You can talk about n to the n to the n. You can talk about n to the n to the n to the n times. There are sequences that go to infinity very, very fast. By and large, to show that one of those things, or 1 over one of those things, is a convergent series, life is easy, because you're bigger than exponential. I can compare you with a geometric series that converges. If you're bigger than polynomial, I can probably show you're bigger than some p series that converges, right? The things that are way out there are hard to understand. It can be hard to compare them to each other. n factorial over n to the n. Does this converge? That's a very hard example. We'll talk about that one later. I think it's in your homework, but I'm hoping someone will do it and we can talk about that example tomorrow. Speaking of which, I told you by text, but in case you haven't looked at that text, please write up some homework and turn it in for tomorrow. I want to be able to talk about student work. It sucks having your work talked about. Like especially to the nitpicky level that I'm going to be getting at, thinking about you use this word instead of that word. Could this have been better? Is this sentence really getting at what you want it to get at? But I think you gotta just look at this stuff to learn it. And you don't want the first time someone judges your sentence construction to be when I'm grading your exam. Like you want to get some feedback before then, and we might as well all learn from each other's feedback. Okay, so there's polynomial speed. There are things that are slower than polynomial speed. I can talk about n to the 0.99, and n to the 3/4, and n to the 1/2, and n to the 1/10. These are all, in my head, I sort of have them all organized as variations on root n. Root n is nice because I have a picture in my head of what root n looks like. It's less than y equals x. It still goes to infinity on the right, but it goes there slowly. These are all powers of x. They don't count as polynomials because, like, once you're down at a fractional speed, you kind of behave differently than a polynomial. I guess by and large, you really want the barrier between y equals x, something that's smaller than x and something that's bigger than x. I guess it's the difference between concave up and concave down, maybe, but these behave differently. These are smaller powers of x, or of n. And we have things that are slower than even those. There's log n. There's log n. I can throw in more logs. If you want something that goes to infinity very, very slowly, what happens if I take log n, where I do it n times? I'm not sure that goes to infinity anymore. That probably doesn't go to infinity. I'm sure there are sequences that go to infinity slower than any of the log n's. I don't know if I can write one down off the top of my head. That's sort of the worst that it gets for this class most of the time. We will see n to the n. Like, these are things that are, well, n to the n to the n, n to the n to the n to the n. These are like correspondence of log n, kinda, I guess. Yeah, so this is the picture I want to have in my head of functions that go to infinity, or sequences that go to infinity. I want to have a good understanding about the idea of these speeds. And this is the kind of thing I want to compare something against. When you hand me the series, something over n to the n plus n factorial, and stuff on top. I want to be able to look at the bottom and say, well, n factorial is smaller than n to the n. So this thing is about as big as n to the n. The n factorial is much smaller than the n to the n, so that is the important term of the bottom. When you add two things and you want to say how fast does this go to infinity, the important one is the bigger one. Because if you go out far enough, if this thing is infinitely bigger than that in the long run, then the smaller one is contributing 0% of the total of the bottom. So here's a place where this is about the same size as that, and the ratio really is true. As opposed to this, where I say that n to the 3/4 log n to the 6 is about the same size as n to the 3/4, but that's not really as true as it was in the other case, because it really is bigger. Log n is a thing that goes to infinity and can make the difference between convergence and divergence, like we just said. Okay, so that's enough of that detour. How am I going to work this problem? The reason I did that detour is to understand that there's nothing magical about 3/4. If I change that 3/4, so like this thing is less than this, and being less than that means that I can't use direct comparison and I can't use limit comparison. What I really want to say is that you're bigger than something, so I want the denominator to be a little bit smaller. Like, there's a good chance we can just use the integral test here. But if you make it a little bit grosser, there's a good chance I can't use the integral test anymore. What is this thing bigger than? I want to make the denominator bigger. I want to make the denominator bigger, even though I want to get rid of those log n's. I want to just turn this into something that's easy to understand. And the key thing, the thing that helps me get that, is there's numbers between 3/4 and 1. I can change that 3/4 into a slightly bigger fraction and still have it be a divergent p-series as long as I don't go past 1. So I'll go to, like, what's bigger than 3/4? 4/5? Does that work? Yeah, anything bigger than 3/4 should work. I think this inequality is true. Why would this inequality be true? Because I want for n to the 4/5 over n to the 3/4 log n. Oh, there's only one log. Log n to the 6th should be bigger than 1. Is that true? Well, these are both powers of n that I can reduce. 4/5 minus 3/4 is, what is that, 1/20th? That'll be true if n to the 1/20th over log n to the 6 is bigger than 1. Is that true? Yeah, I think so. I think any power of n is bigger than any log n. This is why this chart was big in my head. Any power of n is going to be bigger than any of these logs. Which means the gap between n to the 3/4 and a slightly bigger power of n is still big enough to be bigger than all those log n's there. Alright, now it comes down to the writing. I think I've got an explanation. Because 1 over n to the 1/20th over log n to the 6th is bigger than 1, that this should be enough to convince me that direct comparison will eventually work, or maybe limit comparison's the easier thing to do. This fact seems like the essential thing to get me to that this is true, which will get me to convergence. And I want to get this into a write-up. One of the key things here is, how do I show that this thing's eventually bigger than 1? I think the limit is infinity. That would be enough to know that it's bigger than 1. How would I think about the limit as n goes to infinity of n to the 1/20th over log n to the 6th? L'Hopital's rule, the top goes to infinity, the bottom goes to infinity. But geez, if I take L'Hopital's rule, the derivative of the bottom is going to be 6 log n to the 5th. I would have to take the derivative of the bottom 6 times to get rid of the log n's, is the time that I can do the limit directly myself. That's rough. I'd kind of like to just sort of point to the chart and say, look, it's smaller. It's smaller than those, but like you can't do that. The chart is a thing in your head, is for organizing information, is not a reference you can pull out and cite, like a dictionary or something. It's good to keep in mind that you can do basic things with functions. To know that this is going to infinity is the same as knowing the 6th root of the thing goes to infinity. Let's take the 6th root of the whole fraction. That's n over 1 over 120 versus log n to the nothing. Ah, now I can use L'Hopital's rule a lot simpler. Derivative of the top, derivative of the bottom. This is one I can do immediately all by myself. Awesome. Cool. So I think if I try and write up a paragraph about this, it'll be good to start with using L'Hopital's rule on this. That'll be my big piece of gross math stuff that happens outside. And say, since this goes to infinity, when I raise it to the 6th power and get this, that'll go to infinity. Which means that this is eventually going to be bigger than 1. I guess I'll multiply the top and bottom by n to the 3/4. Which gives me this inequality, which, there we go. Awesome. You can sort of write this in any order. There's versions of this paragraph where I say, I want to show this, and it's enough to know that, and it's enough to know that, and it's enough to know that, and now we'll use L'Hopital's rule. You can write that out. That's a paragraph people can understand. I feel like if the flow of logic is this, therefore this, therefore this, therefore this, to my mind it's easier reading if you present the hypothesis and work your way to the conclusion. And I know that that's wrong. Like, my instinct is to start with this and build out of that. The reason that that's wrong is, where did this come from? You're pulling this crazy limit out of your butt that has nothing to do with the original problem. Why are you doing that? It's easier, like, you got to keep in mind two different versions of why someone's reading this. If someone's reading this to be good at doing these problems, it's better to start from this end and build your way up to, that's why I came up with doing this weird limit, and this weird limit I can do with L'Hopital's rule. That is the easier thing for the person reading you to get better at doing problems with. Like, me as the teacher, this is the best way for me to present it to you, and it is the way I presented it to you. I didn't start with, well, I'm going to grab this and do blah, blah, blah. The other reason I want to write out this paragraph isn't so that you can understand how I did it. I might be trying to write this so that you can verify that the steps I am doing are correct. And in that sense, I think it's easier to write it starting from the weird pull it out of your butt L'Hopital's rule problem to do, and building up to the correct problem from that. And you kind of want to understand which thing you're writing for. If I'm presenting the problem to you right now, me as teacher showing you student, how can you do this problem, going in this direction is probably the better thing to do, and I just did that as my scratch work. Now me writing a paragraph as if I was the student trying to convince you that I've definitely verified that this thing is definitely true, this is the better direction. I'm not telling you to write it one direction or the other. You can totally write it the other way. Many of the examples you'll read in textbooks or see other teachers do will present it to you in that way, because that's the better thing for students to understand. But I think the better thing for giving a proof that the thing is true is to start with the weird thing that you pull out of your butt and build the problem out of that. So, let's try this. Let's say the problem was given to us as this. Also, hey, just heads up, when you turn in your exam, present your scratch work also. Like, it's not part of your paragraph, but you're giving me chances to give you points, which is, a completely separate thing from writing a good paragraph. We're going to start by consider the limit as x goes to infinity of, what was it? It was x to the 1/20th over log x. Is the start of our explanation. Using the infinity over infinity version of L'Hopital's rule, I think there's an accent on the A in L'Hopital's rule also. Do you guys know the story of L'Hopital's rule? I should save that for after this example. Using the infinity over infinity version of L'Hopital's rule, this equals the limit as x goes to infinity of 1/20th x to the minus 19 over 20 over 1 over x is the limit of 1/20th x to the 1/20th when you combine those powers of x equals plus infinity. Cool. If the function goes to infinity, then raising it to the 6th power goes to infinity also. A big number raised to a positive power is still big. Here's a good place to switch from talking about the function to talking about n. Actually, yeah, let's phrase that. F of n to the 6 goes to infinity also. The limit is n goes to infinity. Like, I need to make that transition also. Here's a nice place to do I'm being a little bit over-explainy here, so it's reasonable to 6 over 20 ln x to the 6. Have I messed this up? Was it supposed to be 6 over 20 on top? Oh, no, it's supposed to be 1 over 120 on top of the original version. This is supposed to be the 120. Ugh, okay, let's fix this. That was supposed to be 1 over 120. So this is 119 over 120. This is 1 over 120. X to the 1 over 120 is plus infinity. Cool. Any positive power of x goes to infinity on the right. Cool. Now I have x to the 1 over 20 over log x to the 6 equals the limit as n goes to infinity of, I want to multiply the top and bottom by x to the 3/4. Was it x to the 3/4? I'm sort of losing. I gotta check my scratch work. What was the point of this? I want to end up with an inequality like this, either in a ratio or in a thing. Yeah, I'm going to put a 3/4 on top and bottom to get this, and then jump from there to there. Okay. So yeah, I'm putting a 4/5, no, 3/4 on top and bottom. I'll end up with 4/5 on top. Cool. 3/4 log x to the 6 equals the limit as n goes to infinity of 3/4 times 1 over 120. 15, 16 over 20 is 4/5. X to the I meant to make all these n's, not x's. At some point I have to transition from talking about the function to talking about the sequence, and I was trying to do that here. Don't use the eraser to underline what you're talking about, Andy. So f of n to the 6 goes to infinity. Here is the place where I'm making the transition from function to sequence. I'm trying to do it without saying out loud that I'm doing it, but it's got to happen at some point. This is n to the 1 over 120. Yeah, n is what I meant to say on all these. So I get the limit as n goes to infinity of n to the 4/5 over n to the 3/4 log n to the 6th. Why am I switching between sequence and function? I can't talk about the sequence and use L'Hopital's rule. You can't take the derivative of a sequence. So at some point I have to be talking about the function. At some point I'm going to have to transition from the function to the sequence. This is a really insubstantial step that I don't feel like I need to spend 3 sentences explaining that because the function has this limit, the series has this, the sequence has the same limit as well. But I should mention it a little bit. When I'm taking the 6th power of the sequence, so what I'm really doing here is burying 2 steps in one. I'm saying that since f of x goes to infinity, f of x to the 6 goes to infinity, and f of n to the 6 also goes to infinity. I'm taking a 6th power and converting function to sequence. Okay, and it's worth mentioning that I'm like finding a way to squeeze that in. So this limit equals this limit equals this limit equals plus infinity. It's a little bit obnoxious, the ordering here. I mean, here's a place where the reasoning is happening backwards. This thing I know is infinity, and from that I'm concluding that that thing equals this thing equals that thing must also be infinity. But it sort of looks dumb to say start with the plus infinity on the left, which is probably the more reasonable. Like, on the one hand, starting with the infinity on the left means now that's in the logical order. We know this thing equals infinity, and it's very clear that this equals this equals this. That would be an easy way to read it, except it looks really ugly to say infinity equals. Like, you want to end with the plus infinity. I don't know why. Maybe you don't want to. I want to. It feels prettier to me to write it that way, like, more reasonable. I feel dumb starting a sentence with infinity equals this. Like, that feels weird. Maybe it would be better to start with this thing and say this, you reduce the 3/4 and get to this, which is infinity. That might make more sense to write this first equals this thing equals this thing equals plus infinity. And you could make a case that that's the way you should do it. To me, it feels like another example of pulling things out of my butt, though. Like, why are you pulling this thing out? Oh, it turns out to be the same as this thing that we just said equals infinity. Okay. To me, the better reasoning is to start with this thing, which we just said is infinity, is all this, which means this thing is infinity also. Like, there's an inflection in the middle of this where you say, this thing we know can be rewritten as this and this and this, which must therefore be the thing we know. Like, there's a whole little turning the corner point here. I think this is clear enough, and to me, this is the best way of the flow of information to go. This is how I like writing it. I'm not saying this is the perfect way. I'm not saying this is how you have to do it, but this is the kind of thing you want to be thinking about when you're assembling these sentences. All right. That equals infinity. In particular, it's eventually greater than 1. So 1 over n to the 3/4 ln n to the 6 is going to be bigger than 1 over n to the 4/5 eventually. Direct comparison applies. Or I don't want to say direct comparison applies because I like folding that into the sentence. This gives immediately. Immediately is a word you throw in to say, surprise, we're done. That the sum of 1 over n to the 3/4 log n to the 6th diverges. By direct comparison, with a natural way to phrase it with the series sum 1 over n to the 4/5, which is a divergent p-series. I want to say it. I need to show that it diverges. The reason it diverges is that it's a p-series. Saying that it's a divergent p-series lets me get both of those facts in one little like turn of phrase. And then I like being cute and smushing all this together and saying with the divergent p-series. But like that might be that might be too cute. This is the more normal way to phrase it. Ugh, this is gross. Look how much stuff we packed in. So what did we do here? We off to the side worked out how the inequality we want. So A, we had to be creative and come up with the fact that a power of 3/4 doesn't work for a comparison test. But if I jump that 3/4 up a little bit here to 4/5, Now I have something where the denominator is even bigger, so the fraction's even smaller. Changing the 3/4 to the 4/5 gives us enough room to jump past all those log n's, right? The difference between them is n to the 1/20th, which is bigger than all the log n's, so yeah. Then we have to figure out, well, what that really boils down to is we need to know that this thing is bigger than 1. We could use L'Hopital's rule there 6 times, but that's more work than I want to do. I can get rid of the power of 6 by saying, like, the sequence will go to infinity if and only if its 6th root goes to infinity. Just take a 6th root, and now we only have to use L'Hopital's rule once. Part of what's going on here is when you're doing the limit comparison tests, you have a lot of room to throw garbage away. Let's try an example that shows that a little better. Consider this, or don't say consider, that's how you start a paragraph. I'm just handing you this series, and you're gonna do. I'm handing you the series with, that's not what I wanted to paste. With the instructions, determine whether the series converges, diverges, if it's alternating, do that other stuff too. Let's talk about the sum of n squared minus 2n plus natural log of n under n to the 1/4 minus log n to the 6th plus n to the 1/19th. About how big is this? I want to show this converges or diverges. I got so much garbage on the top and bottom. What I really want to be able to do is throw away as much garbage as I can. The top, I have log n is very small, smaller than any power of n, so this is the least significant term on top. I have n to the 1/4 and n to the 1/19th. The bigger power will be the bigger sequence, 1/4 is the bigger fraction. So the top is about n to the 1/4. How big is the bottom? The bottom is, I have an n squared, I have an n, I have a log n. The biggest of those is n squared. This fraction should be about the same size as n to the 1/4 over n squared. What is that? That reduces. That's 1 over n to the... What is this? This is 8/4. So this is 1 over n to the 7/4. That's a convergent p-series. Here's a low-level way of thinking about it. The way we've done things like this in the past was to say, I hope that this is less than this. Is that fraction less than this? To make for the fraction to be less, we want to know the top got bigger, the bottom got smaller. But let's not reduce that 1 over n to the 3/4. Let's explain why this is a reasonable comparison. Did the top get bigger? Throwing away this did make it bigger. Throwing away that did not make it smaller. So no, that did not work. I don't get to say that it's immediately less, so I'm stuck doing limit comparison. And limit comparison will work. Limit comparison will turn this into, if you eventually do the right things, this divided by n to the 1/4 over n squared will be, you're dividing by n to the 1/4 on top. You gotta verify that this thing goes to 0 and this thing goes to 0, and you have, the limit is gross, is the point that I'm getting at. And limit comparison is the stronger tool, but it's the harder tool in a lot of ways. Like, it works when direct comparison doesn't work, but doing those limits is gross. So instead of thinking in terms of limit comparison, I want to show you how to get good at throwing away pieces creatively. What I'd like to show is that n to the 1/4 minus ln n to the 6th plus n to the 1/19th. I want to show this is less than something. That means I want to increase the top and I want to decrease the bottom. Okay, so I can throw some things away right away. This thing, gets thrown away. Not subtracting something makes the top bigger, right? This part I'm leaving the same because that's the important one. You are bigger than if that was a 0. Cool, I have made the top bigger, that makes the fraction bigger. This thing I can't throw away, and instead I want to make it bigger in a way that makes the entire fraction easy to understand, and the cool trick you can do is to say that thing is smaller than 1 over n to the 1/4. If instead of n to the 1/19th there, I had n to the 1/4, I have made the fraction bigger, and this thing is going to combine into 2n to the 1/4. It's okay if there's a 2 on my p-series, I still understand that that means the p-series converges. Here's a really nice way of throwing terms away by saying, well, I can't... To make the top bigger, I need to make this bigger. I could make it smaller by changing it to 0, I could make it bigger by changing it into n to the 1/4. Either of those works to help me understand that this thing is basically the same size as n to the 1/4. I'm worried that I'm talking crazy talk. These sentences are so hard to dive really deep into the details of a piece of reasoning here. Alright, I want to keep making the fraction bigger. I've dealt with the top. I've turned the top into something simple that I can understand that's basically going to turn out to be a p-series. To continue saying this is less than this fraction, I need to make the denominator bigger. The n squared is fine. Actually, I can change that into 2n squared. If I wanted to. I could change it to 20n squared. I might put the 2 there to cancel with the thing there. But the key thing is I want to embiggen the fraction. Oh, no, I can't put the 2 there. I want to ensmallen the denominator to make the... I want the fraction to become bigger, so I need the denominator to become smaller. Okay, I can replace the log n with a 0. Log n is big, changing it to 0 makes it smaller. I also want to make this 2n bigger. Well, if I did what I did here, I would want to say minus 2n squared. But this is no good because now that makes the fraction negative, and I don't want to let anything go negative. Okay, I can't change it into 2n squared. How about a half n squared? This works, but is obnoxious. Just saying that 2n is smaller than half n squared. This is a fact that hopefully is obvious to you because n squared is a bigger power of 2, like the power of n is more important than the constant out front. But it's now the type of piece of reasoning that I feel uncomfortable asking someone to know is immediately true off the top of their heads. Changing this to a 0, yes, you have made the top bigger. Changing this to an n to the 1/4, yes, you have made that bigger. Changing log n to a 0, yes, you've made that smaller because log n is positive. Changing 2n to 1/2 n squared, this is now, to my mind, just a step too big to do without justifying. It's a great step to use, because now I'm going to have 2n to the 1/4 over half n squared is 4 n to the 1 over n to the 7/4, which is basically a p-series, and I can talk my way out of the rest of that. The only step that's stopping me from doing this direct comparison right now is how can I change the 2n to a half n squared? Can I do that? Yes, I can, but I want to... All of this is getting to the point where justifying me saying that I want to add a sentence that 2n is less than half n squared. It's true, it's obviously true, but it's not so obviously true that I want to say it that I want to use it without saying it. Right? So let's paste. Let's start doing a paragraph. If I'm going to use direct comparison, I need the series to be positive. Maybe that should be the first thing I write out. These terms are eventually positive. Oh, maybe I should think about what's the first value of n where the denominator is never 0? Can I start at 1? That's actually 0 at 1. I should start at n equals 2 or 3. Let's start at 10 and not be stressed over it. These terms are eventually positive. Is that obvious? N squared is eventually bigger than 2n. And why is the top positive? N to the fourth, n to the 1/4 is eventually bigger than log n. Maybe it's always bigger. I'm not sure. I don't have a good graph of those in my head. Ooh, n to the fourth, 1/4 being bigger than log n. Is that obvious enough for me to say without doing? Like, I had to write out a L'Hopital's rule to use a statement like that just a second ago. Like, here's a thing that, ooh. Here, because there's enough other stuff going on, I feel comfortable not justifying this. But maybe I should. Maybe I should be using L'Hopital's rule. Yeah, n to the 1/4 is eventually bigger than log n, for example, by applying L'Hopital's rule. To x to the 1/4 over log x. I'm not going to actually write out the L'Hopital's rule, but I can at least point you to a way of showing this. I'm going to go back to putting spaces between these because that's way easier to read, I think. I shouldn't have bunched all these up together. These terms are eventually positive. We have, since 2n is less than half n squared eventually, it follows that eventually we have n to the 1/4 minus log n to the 6th plus n to the 1/19th over n squared minus 2n plus log n is less than, I want to make the top bigger, n to the 1/4 minus 0 plus n to the 1/4 over n squared minus half n squared plus 0. I'm able to make statements like this. Like, this is kind of a big step that you might feel uncomfortable writing out, but you can trust your reader to understand. We made the denominator bigger, clearly. The top is now greater than it was before. We changed something negative to a 0, that makes it bigger. I changed n to the 1/19th to an n to the 1/4. 1/4 is bigger than 1/19th right away, yes. I changed the log n to a 0 on bottom. That made the bottom smaller, that makes the fraction bigger. I changed the 2n to a half n squared. This is the one that's not obvious, but I just justified that in the last sentence. 2n is eventually less than 1/2 n squared. This inequality isn't necessarily always true, but it's eventually true, because n squared is bigger than n, because we know how polynomials work, because we're in calculus. We have this, which equals, what did we say it was? 4 times 1 over n to the 2 minus a fourth is 7/8. It's going to be tempting to show out your simplification here, but this part's easy. Doing from here to here is like careful and crafty. This is something a high school algebra student can do. You're allowed to just say, here's the answer you're going to get when this simplifies. So, since the sum of 4 1 over n to the 7/8 is, it's not quite a p-series, it's a constant multiple of a p-series. I like being precise about that language. guess I won't put convergent in parentheses because it's like important and worth stating. I might put is a constant multiple of in parentheses. This thing isn't quite a p-series, but it's basically a p-series, and everyone looks at that and says, "Ah, that's basically a p-series." So I don't want to say it is. You don't want to say is basically a p-series. That's the kind of math language that feels very imprecise and not good. Since this thing is a constant multiple of a convergent p-series, the given series converges as well by direct comparison. Hooray! We got a paragraph. Cool. Stuff's hard, guys. What else do I want to talk about? I haven't done enough alternating ones. I should do some alternating ones. Oh, I want to do one of these too. I said a second ago that n to the 100 is way smaller than n factorial. So it's reasonable for me when I look at that to say, hey, the top is way smaller than the bottom. Is the gap between those big enough to know that this converges? I guess I don't really... That doesn't immediately follow. I would guess that it is, because like when the things are big, having something be bigger than something else probably means it's way, way bigger than something else. But I don't really need my intuition here. My intuition that this is bigger than this would be helpful for me to come up with a good comparison test to use. The fact that there's a factorial here is probably already telling me I'm going to do the ratio test. Let's just do the ratio test. Consider... Let's actually not do this in a paragraph. Let's just write out the limit. Limit as n goes to infinity of... Or... I guess I should give that. Let an be the name for n to the 100 over n factorial. The limit... The reason I'm giving a name to this is I want to make it clear that in the ratio test I do an plus 1 over an. And it doesn't make any sense to write this down unless I've said what an means. The limit of the n plus 1th term over the nth term is the limit as n goes to infinity of n plus 1 to the 100 over n plus 1 factorial over n to the 100 over n factorial. That becomes the limit of n plus 1 to the 100 times n factorial over, I'm going to put matching next to matching, n plus 1 factorial and over n to the 100. This thing can become n plus 1 over n all to the 100. This thing can become 1 over n plus 1. This is the deal where n factorial over n plus 1 factorial means multiply all the numbers through n over multiply all the numbers through n plus 1. Those are all there, everything cancels except the one extra one that the bottom one has. You want to be able to do cancellation like that. This is why the ratio test is good with factorials. I can do this limit. N plus 1 over n, pre-cal, polynomial, same degree on top, is 1 to the 100 times 0 equals 0. Since 0 is less than 1, the given series... I guess I don't even need the word given here because there's only one series we're talking about, but it seems good to include it. The given series converges by the ratio test. The ratio test is the one that usually needs the least writing. If the series had pluses or minuses on it, I would want to mention the word that it converges absolutely. The series is all the way positive, so converging automatically means converging absolutely, because the thing is its absolute value. So the difference, what converging absolutely means is it converges if you put absolute values on it. And if the thing is positive, putting the absolute values doesn't mean anything, is why these instructions we talk about don't care whether the thing is positive or negative. Here's a gross problem. Let's consider... Yeah. The root test also, usually there's nothing really to write about. Although the limits can be difficult. Let's do the sum from n equals 1 to infinity of cosine of n pi over 3 over n factorial. What is cosine of n pi over 3? What does n pi over 3 look like? I'll draw my Trivial Pursuit circle. Cosine of n pi over 3 is, first it's a half, then it's negative a half, and then it's 0. And then it's negative a half, and then it's positive a half, and then it's... Oh no, it's 1. And negative 1 here. What is going on here? I get 1 half over 1 factorial minus a half over 2 factorial minus 1 over 3 factorial minus a half over 4 factorial plus a half over 5 factorial plus 1 over 6 factorial. So my numerators are going to be a half, negative a half, negative 1, negative a half, positive a half, 1, positive a half. Ugh. Ugh. This is so gross to try and understand. It's not an alternating series. To be an alternating series, you have to be strictly plus minus plus minus plus minus. This one is plus 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 minus 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 plus 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 minus minus minus. I can't use the alternating series test on this. Hopefully it's not that type of deal. How do I deal with that? The main thing going on is that 1 over n factorial on bottom is super big. The top being sometimes positive, sometimes negative is kind of irrelevant, because the bottom goes to infinity so fast that there's no way this thing converges. So... that means if the plus minus issue wasn't there, this thing probably converges, right? If I just had 1 over n factorial, I think that converges. How would I show that converges? I guess anything with a factorial, I like the ratio test. I wouldn't want to use the ratio test on this, because the 1/2 and the 1, like, I don't know how to deal with that ratio. It's either... maybe there's a trig identity for dealing with cosine n plus 1 pi over 3? I don't really want to do that. I'm going to do this in 2 steps. I think the thing converges absolutely, because if I throw absolute values on it, the cosine, like, here's a nice thing to know about sine and cosine, is they don't get bigger than 1. Like, when I'm trying to understand how fast they go to infinity, sometimes they are 0. I guess this one is never 0. So if I'm dividing by sine and cosine, that's a little bit of an issue. But when you're multiplying by them, they're never worse than 1. So, I want to do 2 steps. I'm going to show that the thing converges absolutely. Because this thing has some positives and some negatives, we care about absolute versus conditional convergence. I'm going to say that the cosine... absolute value cosine n pi over 3 over n factorial is less than 1 over n factorial. Everybody knows sine and cosine are less than or equal to 1. So I get this for free. This is going to be a direct comparison to turn that series into something easier to understand, and then I'll use the ratio test on that. Cool. In this situation, I like making a paragraph sandwich. I guess I would do math stuff to show the inequality. Then I would write text to say, that means the series you gave me converges if I can show that 1 over n factorial converges, and I will show that 1 over n factorial converges by using the ratio test. Now I do gross math stuff to show that this thing converges by the ratio test. Like, I don't want to... I've been doing examples where when I have some gross computation to do, I put that before the paragraph. Here, there's like 2 big pieces of computation. I like putting the paragraph between them. You want some text touching some text, but I don't really need to do 2 paragraphs if I point up at the top and point down at the bottom. And I guess I don't really need a big math display to do that inequality, that's obvious. We have that absolute value cosine n pi over 3 over n factorial is less than or equal to 1 over n factorial. So we will have that the given series converges absolutely if we can show that the series sum 1 over n factorial converges, which we can show, which we can do by the ratio test. Colon. Now I'll just do that limit. I want 1 over n plus 1 factorial over 1 over n factorial. This is the limit of n factorial over n plus 1 factorial. This is the limit of 1 over n plus 1. This limit is 0. Maybe I'll mention which is less than 1 is the important part about 0. Cool. Are there any hypotheses about the ratio test I should have shown? No, the ratio test works on any series. I don't even need it to have positive terms. I guess maybe I should have had absolute values on this as the technical statement of the ratio test, but everything inside is positive, so those absolute values don't matter. Yeah. Note that I need to be using the word absolutely here because I'm showing not just that it converges, it has positive and negative terms, so I need to show that the question is, does it converge absolutely or conditionally? And here it does converge absolutely. Alright. Let me do one more bad one. Sum from j equals 1 to infinity of negative 1 to the j root j over j plus 5. This is not a series of all positive terms. So, and it's not all negative terms either. And it's not eventually positive, it's not eventually negative. I have, this one is just alternating. I need to know, does it converge? And if it converges, is it absolute or conditional convergence? About how big is this? If the negative 1 to the j wasn't there, this would be about as big as root j over j is 1 over root j. Does the sum of 1 over root j converge? That's a p-series. That's 1 over j to the 1/2. 1/2 is less than 1. This series diverges. You really want to know the p-series and geometric series facts right off the top of your head. That series diverges, which would make me think our series diverges, but wait, our series is alternating. That says that our series, so I want to conclude that our series doesn't converge absolutely. I don't know that it doesn't converge. I only know that it doesn't converge absolutely. Is my stream still going? Hooray, I'm still alive. Cool. Does our series converge at all? The difference between it converging at all and not converging at all is if it converges, I'm probably using alternating series test. If it doesn't converge, I'm probably using the divergence test. Remember, alternating series test just needs us to know that the sequence goes to 0 and is decreasing. Almost all the time, if you go to 0, you get decreasing for free. Like, hopefully, we don't have to deal with a situation where that difference matters. The divergence test is if it doesn't go to 0, it diverges. So this is basically the dividing line for an alternating series between divergence and convergence. Do the terms go to 0? If they do go to 0, then the sum of -1 to the an converges. If they don't go to 0, then with or without the -1 to the n's, they don't go to 0, so the series diverges. There's a little tiny bit extra that we need to know that it decreases, but you almost always get that for free right away. We've mentioned a couple examples where you don't get that for free. Right. That's the main question, is does the limit equal 0? Well, the limit of 1 over root j does go to 0. So root j over j plus 5 probably does too. Yeah, that's a limit I can work out. So, So it's conditional convergence. Conditional convergence is the worst one, where we have the most writing to do. Our hope was that if the limit wasn't 0, then we never have to write this out. Or if this thing converged, we would never have to write this out. We're in the middle case where we have to show you don't converge absolutely and you don't diverge, blah, 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 convergence conditionally. Let's start writing that out. Let's, I guess, do this one first. We want to show the series doesn't converge. Absolutely. I guess I should write out why. Because, well, I mean, I need to write out how am I going to show that it doesn't converge absolutely. I want to say that root j over j plus 5, I want to compare that with root j over j. This series I know diverges by, because it's a p-series. So if I want to show this diverges, I'm hoping it's bigger than that. To make the fraction bigger, I want to make the denominator smaller. Hey, throwing away the 5 does make the denominator smaller. If it didn't make the denominator smaller, or if that was the wrong direction, I would change the 5 to a 5j. And now the whatever. Like, you can kind of get it both directions. This is kind of what I mean when I say that. N squared log n lives between n cubed and n squared. Most of the time, you don't care if you have an n cubed or an n squared. They're both going to be a p-series. They're going to be a thing I understand. So n squared log n is not a polynomial, but I can sort of compare it with a polynomial that's bigger. If I want you to be smaller than a polynomial, I can compare it with a polynomial that's smaller if I wanted it to be bigger than a polynomial. That's the kind of trick that we're allowed to make. This series doesn't converge absolutely because I should mention the sum j equals 1 to infinity of the absolute value of the terms. Equals the sum of root j over j plus 5 and root j over j plus 5 is bigger than root j over j equals 1 over root j. Here it's tempting to sort of close off my sentence and say which is a divergent p-series. I can't do that. Why can't I do that? Because this thing's not a series. I'm talking about a sequence. I'm talking about the terms. This thing isn't a series at all. So I don't get to like jump there right away. This thing is bigger than this equals this, and so our series diverges by direct comparison. I smush those words together with the divergent p-series sum 1 over root j. Oh, this is really bad. Notice a terrible thing I did. Our series? What do you mean by our series? Probably by our series you mean this one, right? That's the one we're trying to talk about. This isn't the thing that diverges. The thing that diverges is this series, which I don't have a really good way to give a name to. I probably just need to write its name out again. So I need to fix that by saying sum j equals 1 to infinity, root j over j plus 5. Diverges by direct comparison with the direct divergent p-series sum 1 over root j. Now I'm tempted to sort of write a conclusion. Thus, the given series doesn't converge absolutely. But if I look back, I already said, like, this is saying the exact same thing as this first clause. This doesn't converge absolutely because, and that was like 1.5 sentences ago, so I don't really need to restate that. We got that. If I had, like, if this was a long page and a half between here and here, yeah, restate the conclusion. This is 2 sentences ago. Yeah, I don't need to restate the conclusion. People remember we just said that. But the given series does converge. By the alternating series test. Yeah, I'll write out the words alternating series test. Since root j over j plus 5 is positive, what do I need? It's positive. The limit is 0. Yeah, I can say the limit is 0. I guess I should write out why I know the limit is 0. I guess the standard way to do it is multiply the top and bottom by 1 over the biggest thing on bottom. 1 over j over 1 over j. Like if I did 1 over root j over 1 over root j, I would have 1 over infinity is my reason that it's 0. Saying 1 over infinity is bad form. Saying 0 over a constant is good form. Like 0 over a constant, I don't have to touch the infinities. So this is the better way of writing that. This is 1 over root j over 1 plus 5 over j. This limit is 0 over 1 plus 0 is 0. And it's decreasing. I haven't actually verified that it's decreasing. I'm sort of trusting that when I take its derivative, that'll be negative. Since derivative with respect to x of x to the 1/2 over x plus 5 is derivative of the top, leave the bottom alone, minus leave the top alone, derivative of the bottom. Oh, that's a negative 1/2. This is probably worth putting in its own line. This is going to be gross before it's done. Since the derivative of this is 1/2 x to the 1/2 plus 5/2 x to the negative 1/2 minus x to the 1/2 over x plus 5 squared. Those two terms combine. I'll go ahead and do that in one step, since anyone following me can simplify that. I get this minus 1/2 of that. How do I know this is negative? Because the x to the negative 1/2 term approaches 0. Like that's small and that's big. So the numerator is dominated by the negative x to the 1/2 term, or is dominated by, I don't want to make people think I'm saying x to the negative 1/2. I'm talking about this term. Let's just write out the term. Which is negative and large. What I was really hoping for is everything in sight on top was negative, in which case it's obvious that the thing is negative. Here I have negative terms and positive terms, and I need to explain why the negative terms win out in the end. This dominated phrasing is a way people discuss what's the biggest term. Maybe a better thing to do would be to multiply the top and bottom by an x to the 1/2. Is that easier to understand? Then I have a 1 and an x. It's sort of... Yeah, I think this is fine. We're getting pretty far afield, like using this word dominated feels like a cheat. I should be explaining this a little better. Is there a... Yeah, let's try and come up with a better reasoning for that. If I multiply the top and bottom by 2x to the 1/2, I get 2x to the 1/2, x plus 5 squared. And what do I left with on top? 5 minus x. Yeah, 5 minus x is eventually negative without any explanation needed. Cool. And not only can I say it's eventually negative, I can say it's negative on x greater than 5. Ooh, asterisk. I shouldn't have said that it's decreasing, because it's not always decreasing. It's only decreasing once x is bigger than 5. I need to insert the word eventually. Decreasing. Don't say the thing is decreasing if it's only eventually decreasing. Cool. I'm tempted to write a conclusion paragraph here. What did I say in this paragraph? I said the series converges by the alternating series test, since the terms without the negative 1 to the n's are positive, the limit of the terms without the negative 1 to the n is 0, and the terms are eventually decreasing. That's all I need. The sentence... I kind of want to say, thus the thing converges by the alternating series test, but that happened in literally the last sentence. This has only been one sentence. I definitely don't need that wrap-up. I do want to wrap up now that ties these first two paragraphs together. The first paragraph said the series didn't converge absolutely. The second paragraph said the series did converge. There's nothing else to say. That's the definition of converging absolutely, or converging conditionally. The given series converges, but not absolutely. It converges conditionally. It's tempting to put the word therefore here. I think that's bad form to put a therefore. Therefore is like when you make a logical step from here to here. This isn't a logical step. What I'm doing is using the definition of convergent conditionally. This is just what that word means. So I don't want to imply that I'm making a bigger step than I am with a word like a therefore or a hence or a so. So maybe feels fine. Like so to me doesn't indicate there's math going on, letting you get from here to there. Okay. That is a bunch of examples. Do I have more I want to do today? I think I need to take a break because I am wiped out. Yeah, were these a bunch of homework problems I just did? I just pulled them from my lecture notes. I hope I didn't just do all the homework problems. There's nothing with a J. No, I think I pulled these out of the book when I was lecturing last time. The thing I have in front of me a pile of pages, which is a print off of what I wrote on the board last time I taught the class. And then, yeah. I should double check that this extra stuff is not going to be on the current series, on the current test. I have a practice exam. Blackboard. I guess I'll do this off stream. I think I'm done streaming for today. I might do a longer one tomorrow to make up for this one being a little bit short. Well, I don't know. Do I have a debt to do the right number of hours per day? I don't know if I do. But yeah, okay, please, if you're watching this now, before tomorrow, please send me some of your work. I want to take some student work and put it up on screen so it gives me a better excuse to talk about why you shouldn't use the word therefore here. There's a million writing type mistakes that, I have learned to not make that I need to sort of talk about. The mistakes that students are making. Don't let the exam day be the first time someone tells you that the sentence doesn't make sense in this way, and let other people learn from the mistakes you make too. If everybody turns in things that are amazing, then we don't have as much to talk about, but that's not going to happen. These sentences are really hard to come up with. Right, I'll lecture some more tomorrow at 4. Have a good one.